Before we start, let me ask you something. What if I tell you that reality itself is not fixed? And what if I tell you that an electron does not even have a defined position until you look at it? Now, this might sound like philosophy, but it is not. This is physics. And today, step by step, we are entering in the world of quantum mechanics, a world where particles behave like waves, where probabilities replace certainty, where observation itself can change the outcome of an experiment, where the rules are very different from the classical physics we experience in everyday life. For centuries, physics worked almost perfectly. Newton's law could predict the motion of planets, objects, and even falling objects with incredible accuracy. With a few questions, scientists believed they could explain how the entire universe moved. But then scientists started looking deeper inside the atom, and suddenly nothing made sense. Electrons refused to behave the way classical physics predicted. Energy appeared and disappeared in strange way. An experiment began producing results that no existing theory could explain. So new question emerged. Do atoms follow completely different rules? And answer scientists discovered was shocking. Max Planck made a bold and almost unbelievable assumption. He said that energy is not continuous or smooth like scientists had always believed. Instead, he proposed that energy comes in tiny discrete packets in mathematical form. He wrote the famous equation E equal hf. This means the energy of radiation depends on its frequency, and more importantly, energy is transferred in small chunks rather than in a continuous flow. Imagine climbing stairs. Instead of walking up a smooth ramp, you can only move step by step. At the time, this idea sounded strange and even uncomfortable to many physicists because the single question challenged the foundation of classical physics. But Planck did not realize yet was that this was only the beginning of a much bigger revolution. Then Einstein asked a very simple but powerful question. If energy comes in packets, then what exactly is light? For a long time, scientists believed light was purely a wave. But Einstein shows that light can also behave like teeny particle called photon. Each photon carries a specific amount of energy given by the equation E equal hf, and it also carries momentum described by P is equal E by C. This means light was not just something that spread like wave in water. It could actually behave like a stream of particles. Because of this, light can strike a metal surface and knock electron out of it, a phenomenon known as the photoelectric effect. Suddenly, the nature of light became much stranger than anyone expected. Light was no longer just a wave. But wait, the story gets even more surprising. Then Louis de Broglie asked a very bold and slightly dangerous question. If light, which we always thought was a wave, can behave like a particle, then could particle behave like wave? It sounded strange, but the de Broglie followed the mathematics and proposed an answer. He introduced equation lambda is equal h by p, which means that every moving particle has an associated wavelength. In other words, particles are not just tiny solid points moving through space, they also have wave-like properties. And yes, this applies even to electrons. This idea completely changed how scientists thought about matter. Matter was no longer perfectly solid and localized. Instead, it could spread out like a wave. And once this idea entered physics, it began to change everything. In quantum mechanics, momentum plays a central role in describing how particles behave in classical physics. We are used to writing the kinetic energy of particle as where momentum is simply a number that tells us how fast an object is moving. But when we enter the quantum world, things start to change. Momentum is no longer just a simple value we plug into an equation. Instead, in quantum physics, momentum becomes something much more powerful and fundamental. It is no longer treated as an ordinary number. It becomes an operator, a mathematical object that acts on the wave function of a particle to reveal physical information about the system. In quantum mechanics, we treat physical quantities a little differently than in classical physics. Position is still treated like an ordinary number. You can point to a location and say the particle is there, but momentum is no longer just a simple number. Instead, it becomes something called an operator. The momentum operator is written as p hat equal minus iota h bar d by dx. What this equation tells us is something very deep. To know the momentum of particle, we must understand how its wave function change in space. In other words, momentum is related to the in other words, momentum is related to the rate of change of the wave. This reveals a major shift in thinking. Quantum mechanics is no longer just about object moving around in space. It is about how wave change and evolve. Now we arrive at one of the most fundamental rules in quantum mechanics, a rule that the universe itself refuses to break. The rule is written as delta x time delta p is greater than or equal to h bar over 2. What does this actually mean? It means that we can never know a particle exact position and exact momentum at the same time. If we know the position very precisely, the momentum becomes uncertain. If we measure the momentum very precisely, the position becomes uncertain, and knowing both perfectly at the same time is simply impossible. This limitation is not because our instruments are weak or our measurements are bad. It exists because nature itself imposed this rule. In other words, uncertainty is not a mistake in physics, it is built into the fabric of reality. Schrödinger then asked a very simple but important question. If particles behave like waves, how do these waves actually evolve over time? To answer this, he introduced one of the most famous equations in physics, minus h bar square over 2m d square psi by dx square plus v psi equal E psi. At first glance, this equation might look complicated, but its idea is powerful. Unlike classical equations that tell us the exact position of particle, Schrödinger's equation gives us something different. It gives us a wave function written as psi. This wave function does not tell us exactly where the particle. Instead, it describes the behavior and shape of the quantum wave associated with the particle. But this raises a deeper question. If psi is just a wave, what does it actually mean physically? The wave function itself is not something we can directly observe come from it. It is written as p of x equal modulus of psi of x square. This equation tells us, in other words, by taking the square of the wave function, we obtain a probability distribution that shows where the particle is most likely to be detected. Notice something important here. Quantum physics never tells us exactly where a particle is at any moment. Instead, it tells us where it might be found when we measure it. And this idea leads us into a completely different way of thinking about nature. So let's welcome to the universe of probability. There is one very important rule in quantum mechanics, and it is written as integral of modulus psi square dx equal 1. What this means is simple but powerful. The total probability of finding the particle somewhere in space must always be less than 100%. In other words, the particle must exist somewhere. Quantum mechanics does not make particles disappear, it does not lose them, it only tells us that instead of being concentrated at one exact point, the particle can be spread out over different possible locations. And how that we understand this rule, let us move forward and solve something real. Now imagine a tiny particle trapped inside a perfectly rigid box, unable to escape the wall. In classical physics, the particle could have any energy value depending on how it moved inside the box. But in quantum mechanics, the situation is very different. The allowed energies are given by the equation. This equation tells us that the particle cannot take just any energy it wants. Instead, the energy can only exist in specific discrete level. There are no value in between, just like standing on the step of a staircase rather than anywhere on a smooth slope. And this simple idea turned out to be extremely important because it helps explain why atoms are stable and why electrons stay in specific energy level around the nucleus. One of the strangest ideas in quantum mechanics is that a particle can exist in many states at the same time. Mathematically, we write this as psi equal C1 psi 1 plus C2 psi 2. This means the total wave function can be a combination of multiple possible states, each weighted by coefficient. Before we make a measurement, all of these possibilities exist together in what we call a superposition. The particle is not in just one state, it is in many potential states. But the momentum we measure the system, something dramatic happen. The wave function collapses and only one outcome remains. In this way, quantum mechanics reveal a surprising truth. Observation itself helps determine reality. Quantum mechanics does not usually predict exact outcome. Instead, it predicts average and probability. For example, the expected or average position of particle is written as S expectation equal integral of x time modulus psi square dx. This equation tells us the expected position, which is the average value we would obtain if we repeated the same measurement many times, rather than giving a single defined answer. Quantum physics describes nature using statistic and probability distribution. It tells us what is most likely to happen, not exactly what will happen in a single event. And now we arrive at one last strange idea. In classical physics, if a particle hits a wall that it does not have enough energy to cross, it simply bounces back. Crossing the barrier is impossible. But in quantum mechanics, something very strange happens. The wave function of the particle does not instantaneously become zero at the wall. Instead, it slightly extends inside the barrier, which we write as psi is not equal to 0 inside the barrier. Because of this small but non-zero wave, there is a probability that the particle can appear on the other side of the wall. This phenomenon is called quantum tunneling. It may sound impossible, but it is real and it powers many technologies around us, including transistors and much of modern electronics. In the quantum world, things that seem impossible in classical physics suddenly become possible. Quantum mechanics teach us something profound about the nature of reality. It tells us that reality is not perfectly fixed, that the certainty we experience in everyday life is often just an illusion, and that at the deepest level of nature, probability govern how the universe behaves. The equations and ideas we explore are not just abstract mathematics, they are tools that reveal how the universe truly works. In the end, mathematics become the language through which the universe speaks. This was DibaScience. If you're ready to explore reality even deeper and uncover more of the mysterious behind the quantum world, stay tuned. Thank you so much for watching.